Alright, gang, here we go. This is for physics, Unit 8, Part 1, talking about light. Alright, so Unit 8 is all about electromagnetic radiation. We're going to cover a lot of stuff to do with light. This first little bit should be mostly review, shouldn't be too big of a deal, from stuff you learned in Chem 1, and then just kind of applying the common characteristics between sound and light. Alright, so this won't be too bad. Alright, so here we go. Alright, skip that guy. So electromagnetic waves, all light is made out of electromagnetic waves, and essentially they consist of oscillating, this means they go back and forth, electric and magnetic fields. So up here, alright, we've got some source right here, so this is our source, and then this black line that goes down in here, this is the direction of the movement of the wave. Okay, and then notice that you've got an electric field that's red and it goes up and down, right? And so there's your wave for the electric field, and then you've also got a magnetic field that goes left and right into and out of the screen. Okay, and so this kind of gives you direction or an idea, and notice that the electric and magnetic fields have to be perpendicular to each other. Right? The electric and the direction have to be perpendicular to one another, and the magnetic and the direction have to be perpendicular to one another. So you end up with this. So as long as if you can figure out two of these, the direction of two of these, you can figure out the direction of the third. Okay, fairly easily. Okay. So this is how electromagnetic waves work, and this principle right here, this fact of why they use or how they use electric and magnetic fields is the main reason why electromagnetic waves can travel through a vacuum. Remember, all the other waves we talked about so far, all the mechanical waves that we've talked about so far, previous unit, all needed a medium, a string or air or a solid, water, it didn't matter, right? It had to have something for the wave to actually travel through. Electromagnetic waves are special because they do not need a medium. Okay. Now, because of this, because they use electric and magnetic fields, that means their speed is defined. Their speed is finite. It has a specific value, and this is the value that's accepted currently. Okay. But in our class, we don't really ever need to use this many significant digits. So really, we'll just use this guy here. So anytime you need the speed of light, it's always known as c, and it's 3.00 times 10 to the 8th meters per second. Okay. Now, remember that the velocity of any wave is equal to the wavelength times the frequency, right? And we messed with this quite a bit last unit. Now, because our velocity is set as c, okay, that means our c, it always has to be equal to our wavelength times our velocity, but our wavelength and velocity have to always multiply to equal this 3.00 times 10 to the 8th. Okay, so we can have varying wavelengths and varying frequencies, but they always have to multiply to be this c value. And because of this fact, this allows us to have different types of electromagnetic radiation. All right, so here's the electromagnetic spectrum, okay? And as we go to the left up here, we have increasing frequency, and as we go to the right down here, we have increasing wavelengths. Notice that they're inversely related to one another. When our frequency gets higher, our wavelength necessarily gets bigger, or gets smaller, because they have to multiply to be the speed of light. Okay, so you've got this essentially. You've got like gamma rays and X-rays, ultraviolet. You have the color spectrum here, right? Red, orange, yellow, green, blue, and violet. Notice there's no indigo. There's an interesting history lesson in there about indigo. And then you got infrared, microwave, and then you got your radio waves that your radio picks up in your car, and then long radio waves out here. Okay, this kind of gives you a general idea of what wavelengths and frequencies you're looking for each of these, so you might need to reference this table for some of your practice problems. Okay, and then this kind of just gives you a general idea. So like X-rays, obviously the X-rays we use to examine bones and teeth, so on and so forth. Gamma rays, we use gamma rays examination of thick materials for structural flaws. All right, treatment of types of cancer, okay, food irradiation, so on and so forth. All right, so this is our wave speed equation. All right, pretty easy, pretty much exactly like what you're used to using, okay. All right, so the speed of light is equal to the frequency times the wavelength. We did this a fair amount in Chem 1, so this shouldn't be a big deal. Okay, so it says a range of 6.98 times 10 to the hertz, 10 to the 8th hertz to 7.46 times 10 to the 8th hertz. Once used for analog TV channels, is now used for some 3G and 4G cell phones. What are the longest and shortest wavelengths in this frequency? So we're going to have to do this equation twice. We need to solve for the wavelength. So the wavelength would be equal to the speed of light divided by the frequency. All right, so we're going to do it twice, once with one of these frequencies. All right, so wavelength, we'll just say wavelength 1 is equal to our C value, which is 3.00 times 10 to the 8th, okay, meters per second. And then the frequency, well, we'll use this first one first, because why not? Because it came first, so there's no real big deal. Why not? 6.98 times 10 to the 8th. And remember, our frequency is in hertz, okay? That really means 1 per second. So that's why these seconds cancel, okay? Now, one thing I want you to practice doing is using your calculator so you don't make mistakes in it, okay? So use your E function. So what you're going to do is you're going to find the big way to make the big capital E in your calculator. And I want you to punch it in like this, 3.00 E8, okay, over 6.98 E8, okay. And this, if you do it this way, you don't have to worry about parentheses. If you typed it in like this, you'd have to make sure to put parentheses around this guy in the bottom. Otherwise, you've divided by 6.98 and multiplied by 10 to the 8th, and you'll get a vastly different number, okay, on these guys here, okay. Let me see if I can figure out where, okay. On these, if you have a calculator like this, okay, it's right above the 7, okay. All right, this little comma button, so you'd hit second, comma, okay, and then you'd get that E button. So if we go 3.00 E8 divided by 6.98 E8, okay, you get, we want 3 sig figs, so 0.4297, so 4.430, and because we're doing wavelengths, 0.430 meters. Okay, 0.430 meters. All right, and then the second wavelength would be the exact same math, so 3 times 10 to the 8th meters per second. And then on the bottom, we'd have our other frequency, 7.46 times 10 to the 8th hertz. All right, so 3E8 divided by 7.46 E8, and I get 0.402. So those are our two wavelengths. All right, longest and shortest. So this would be the longest wavelength. This would be shortest wavelength. Not a huge difference, right? That's only like, what, 28 centimeters or so? That's not a big deal. All right, let's do some more practice. It says the middle of the visible spectrum is green light. Calculate the wavelength for the green light if the frequency is 5.5 hertz. So it's the same exact math here. This should be easy. So our wavelength is equal to 3.00 times 10 to the 8th meters per second, and then our frequency is the 5.5 times 10 to the 14th hertz. Okay, and when you're doing these, make sure you pay attention. Sometimes they'll have a subscript, like one of the really common one is megahertz. You'll see that a lot. Remember, mega is times 10 to the 6th. So you might have to convert megahertz to regular hertz in order to do it. So anyway, so we'll do our 3 e to the 8th divided by 5.5 e to the 14th. And you get 5.45 times 10 to the minus 7. So I punch that in, right? E to the 14th. Okay, 5.45 times 10 to the minus 7th. 5.45 times 10 to the minus 7th. And we're in meters for our wavelength. Is that what I got earlier? It is. Oh, but we only want 2 sig figs. Oh, shame. Shame. So really, I got 5.5 times 10 to the minus 7th. Meters. I wonder why I got a different number this time than I did earlier. Oh well. All right. The middle of the audible spectrum is 1.0 times 10 to the 4th hertz, or 10,000 hertz. Calculate the wavelength of this sound in air if the temperature is 25 degrees. Now notice we're talking about the audible spectrum, so this is sound waves. Sound waves are not electromagnetic waves, so they have a different velocity. Remember, we defined, this was from past unit, okay? The last unit, we defined the speed of sound at room temperature as 346 meters per second. Okay, so our wavelength is going to be equal to the velocity. Notice I didn't put c over the frequency. All right, so the velocity was 346 meters per second divided by 1.0 times 10 to the 4th, or 10,000. So we can take 46 divided by 10 to the 4th. All right, and we get 0.035. Good. All right, and then they ask us, well, how much longer are by what factor are sound waves farther apart than light waves? So in order to get that factor, all we have to do is just divide the sound waves by the light waves, right? So we'll take our 0.035 meters divided by the 5.5 times 10 to the minus 7th. Okay, so say 0.035 divided by 5.5 e to the negative 7th, right? I got like 64,000 or so, 2 sig figs, so 64,000 factors bigger. Yeah, some rounding errors somewhere in there. I think I might have been lazy with my rounding before I did it today. All right, so let's take before we talk about this, I just want to talk about light real quick. Let's see, I want a blank screen, a white screen. Okay, and so let's pretend for a second that we have a flashlight. So this is my flashlight. Okay, and and we turn this flashlight on, right? And when we turn on the flashlight, coming out from it will be light, right? And light is electromagnetic waves, so it's going to travel as waves. So it's going to come out like this, right? Right? Look at my beautiful waves. So they're going to come out like this, and we know that these guys, they're going to come out in all ways, right? It's not just 3 of them. There's infinitely many of them, and they're going to kind of move out from the source. And flashlights, they kind of spread out as they go, right? They spread out, and so you kind of do that number. Now, so you can imagine, well, that's kind of an easy way of telling what's going on, all right? Now there's this new definition of something that we need to talk about. And if you take a series of light waves or electromagnetic waves and you connect a line to all their crests, okay, and you can imagine that this line would keep going like this, right? Because there'd be infinitely many until the light stops somewhere around here, okay? And if you connected all the crests of all your waves, okay, like this, and then so crests like this, and you can kind of see how my drawing kind of falls apart because these should be equidistant from one another because they're all the same wavelength, right? These should all be the same distance apart. But anyway, so these guys here, these lines that we've drawn to connect all these crests are called wave fronts. Okay, so you could kind of imagine this as like this is like if you've ever been to the beach or a lake big enough with to have tides, you could see like when the tide comes in, or like the waves come in, they come in and hit the shore. As they come in, it's kind of like this front that moves through, right? It kind of starts back there and kind of moves through, and the wave is coming towards you, and as it's coming towards you, you can kind of see that front coming in, and that front is the line of the crest of the wave that's coming up the beach. Okay, and you could imagine if you're seeing it from the side, you could see the wave come across this way. So that's what the wave front is. But this specifically, we're talking about electromagnetic waves. But in my mind, it's really easy to picture it in regards to those waves that are coming up a beach, and you can kind of say, oh, well, that's the front. And then even then, you can kind of feel it if you've ever been, waist deep or so, or higher on the beach, you can kind of feel it hitting you, pushing you back, and it's that front that's pushing you. All right, so that's kind of nice, that wave front. So that's a good thing. And then there was this guy named Huygens. Okay, let's see, what color should we use? How about green? And he said, well, what if we just took our wave fronts and we just drew lines, okay, that are perpendicular to our wave front. So because these are curved, okay, you kind of have to be, a better artist than me. So you could see how we could draw these lines here, and as long as they're always perpendicular, they're going to go in the same direction, and they're going to tell us what's going on with our wave. You see that? And so these green ones are called rays. Okay, so those are our rays. All right, and so you could see like, well, these rays come off of the wave fronts and they kind of go all directions, right? But they're always perpendicular to that wave front as they come out. Okay, so the wave front moves, and then perpendicular from each of those points in that curve, you have a ray, and those rays are kind of spreading out from your source like that. Okay, so really what we can do is we can, instead of drawing all of this stuff to represent everything going on, okay, with the waves, we got the waves in red, then we got the wave fronts in blue, and then we got the rays in greens. Mostly we don't really care about the waves or the wave fronts a lot of the time, okay? So if we draw, so a lot of times we'll just skip straight to the rays because we know that these other two things are true, and they allowed us to skip these. So really we can just be like, oh, you've got these rays that come out as straight lines from your source, etc. And this principle is really important, especially as we move towards reflections. The next part here, we talk about flat mirrors and curved mirrors and so on and so forth. This idea that light can produce rays, all right, is represented by rays is very important. So we've got this guy here, this idea that waves can be approximated as rays, and this uses Huygens principle. And everything else that we did here, I just kind of explained a little bit more in depth, all right? So it essentially says the exact same thing. So here you've got your wave front, and then you've got your rays that are coming off your wave front. All right, and notice that once we're far enough away, okay, our wave front is essentially a straight line. When we're really, really close to our source, the wave front is curved, but as you get farther, farther, farther away, your wave front becomes more straight, right? The slope of that change becomes less. Last thing here is illuminance. Illuminance is really just like intensity. Remember from intensity from sound when we were talking about intensity, okay? Intensity was equal to the power over 4 pi r squared. Remember. And so we were, with intensity, with sound, we were trying to figure out how much power or how much energy goes through a specific area in a given amount of time, right? And we called that intensity, and we said that humans perceive intensity as loudness. The louder the noise, okay, the more intense it is, and the more energy is put through in the amount of time, okay? Illuminance is the same sort of idea, okay? And it is formula, we use an E for illuminance, okay, and it's just simply the same idea, power over 4 pi r squared, okay, and so the farther you get away, the less illuminated it gets, and that makes sense. Like if I go, I could be at my neighbor's house, right, and in their living room the light would be super bright, okay, but if I go 3 blocks down, okay, the light will not be nearly as bright because I'm a lot farther away from the source. And then, okay, so essentially illuminance is proportional to 1 over the square of the distance, okay? So that's essentially what we're saying here. The illuminance is proportional to 1 over the square of the distance, all right? And then the rate at which light, so this is the difference here. With light, we were talked about watts. Our power was in watts, okay? Remember the units of this guy was in of intensity, let's see, where was it? Was in watts per meter squared. Remember this? All right. Illuminance works a little differently. Our power, the rate at which light is emitted from a source, is called luminous flux and is measured in lumens. All right. So this guy here becomes lumens per meter squared. So it's a little bit different unit, but it's essentially the exact same idea. So then we ask the question here. It says, how bright would the sun appear to an observer on Earth if the sun were 4 times farther from Earth than it actually is? All right, well, our formula looks like this, right? So energy equals, or illuminance equals power over 4 pi r squared, right? If we plug 4 into our radius, because we're getting 4 times farther away, it would be power over 4 pi times 4r quantity squared, which would become power over 4 pi 16 r squared. So notice between these two things, we've got a 16 right there. So the brightness of the sun would be 1/16 of what it is from where we are right now. Okay, whatever that value is. We weren't given that value, but we just know it would be 1/16 as illuminated. Okay, and that's it for part 1. Next part, we'll talk all about reflections and so on and so forth. Should be a lot of fun. Let me know if you have any questions, and I'll see you on the flip side.